In our next section of class here, we're going to begin our discussion of IP version 6. We're going to spend some time talking about the general architecture of the protocol, how the addressing format differs between IP version 4 and IP version 6, then get into the specifics about the routing protocols, how we implement static routing, dynamic routing with RIP, EIGRP, OSPF, and BGP, and then some of the additional tunneling mechanisms that we can use to route IPv6 over the IP version 4 only network, or the reverse path where we can route IP version 4 over an IP version 6 only network. Now, as we know, the main motivation for migrating to IP version 6 is that the address space is much larger than IP version 4. Now, we're not really going to get into the details of the packet level formats for IPv6 and a lot of the RFC level type details. You'll see I have lots of links to the specific RFCs that define those different portions of the protocol, whether it's talking about the addressing or talking about the routing. So if you want to get more detail on those, you can reference the RFCs. You'll see that for a lot of this information, as long as you understand how the addressing works, the principles of routing are going to be almost identical between IP version 4 and IP version 6. So this means that if you really understand how OSPF version 2 works for IP version 4 routing, then you're inherently going to understand how OSPF version 3 works, as long as you can get past the portion of the addressing. Now, specifically, IPv6 uses 16 bytes for addresses, which means it has a range of 2 to the 128, or 340 undecillion addresses, which is just an insanely amount of large address space, where with IP version 4 we have 32 bits, which means that it's about 4.2, 4.3 billion addresses. Now, the notation for the IP version 4 versus IPv6 is where a lot of people get into trouble, especially during the implementation. It's very easy to make a mistake when we're typing in addresses that are so long. Where with IPv4, it's only 4 digits, it's not that many that we need to deal with. But with IPv6, it is denoted in hex, where 2 digits is going to be 1 byte. So we have the 16-byte address that is 8 fields that are separated by colons, where typically the first 4 fields separated by the colons are going to be the network portion of the address, where the last 64 bits are going to be the host portion. Now, per the more recent RFC, which is 4291, that defines what the address allocations are supposed to be, you'll see that it has changed versus some of the older ones that were defined in the late 90s when IPv6 specification was originally coming out. Specifically, the unspecified address is :/128, which is the 0 address. The loopback address, where in IP version 4, this is the 127/8 address. In IPv6, this is going to be :1/128, so it's just all zeros followed by a 1. Multicast is always going to start with FF. So anything with the first 8 bits being a 1, that's going to be multicast addresses. Specifically for our implementations, we'll see that this is going to relate to the dynamic routing protocols that are using multicast for transport of the hello packets and then the updates between the neighbors. We have the link local addresses that start with FE80. This would be the equivalent of the 169.254/16 address space in IPv4. So these addresses are going to be really important for IPv6 because regardless of what the global addressing that we assign on the interface or to the devices, all links are going to have a link local unicast address automatically assigned. So technically anything that is not these first 4, that's the unspecified loopback, the multicast, and the link local range, technically all of the rest of the stuff is going to fall under the global unicast range, which is the actual addresses that would be globally routable on the internet. We'll see the addresses that are left over, it's a much smaller subset that's actually being allocated right now. Generally only addresses somewhere in the 2001, 2000, and then some range after that It's actually 2000 /3 is what's being allocated. So the vast majority of the rest of the global unicast addresses are still currently reserved for allocations that are going to happen much further down the road. Now, the link local addresses, again, are the ones that are going to start with the FE80. We'll see specifically in the iOS's implementation, every time that we turn IPv6 on, whether we are routing it or not, so anytime an IPv6 address is assigned to the interface is also going to get a link local address. Now, this is going to be used for the stateless auto configuration, which for the actual end hosts, like your Windows or Mac OS or Linux machine that's connecting to the LAN, they will use stateless auto configuration in order to learn what is the actual routable prefix that the routers have assigned onto the link. Then they can do the neighbor discovery, which is going to be the replacement for the address resolution protocol, and the router discovery, which is kind of a replacement for DHCP, where without having to do an actual allocation of a pool of addresses, the end host can still figure out who is the router onto the segment and then start to route traffic out to other remote hosts. Previously, there was also another space that was called the site local addresses, which originally were designed to be locally significant within an internal network that were not going to be publicly routable. These are the ones that start with the FEC0 range. So specifically, it's FEC0/10. This was originally defined in RFC in 1884, but now it's been removed. It's been deprecated in a more recent RFC 3879, basically because nobody could agree on what the site definition actually was. So you could technically still use these addresses if you wanted to assign them FEC0. They're not going to be publicly routable in the BGP table. So when a provider is accepting advertisements in, they should be filtering prefixes that would be in this range. Essentially, they are then replaced by what's now known as the unique local addresses. So the unique locals, or the ULAs, these are the equivalent of the private use addresses for IPv4, which is the 10 network, the 172.16, and the 192.168. These start in the FC00:7 range. So either FC, or FD, which are specified in RFC 4193. Now, technically, these addresses are not going to be globally routable in the BGP table, but since the address space is so large, it's pretty likely that the address is going to be unique anyways. So if you take a look at that particular RFC, there's a recommendation as to how the address should be derived based on basically a random number function. And since there's so many bits left over, essentially 121 bits left over for the rest of the address, it's very, very unlikely that two hosts would end up assigning the same address. So this is any address space that you could use internal to your network, where if you were to not get an allocation from IANA. So if you want to do some sort of test deployment without actually allocating addresses, this is what you should then use, is the FC00 range. Now, the global unicast ones, these are the actual public routable addresses on the internet. Technically, again, it's everything that is outside of the unspecified, the loopback, the multicast, and the link local. But allocation-wise, if you look on the IANA website, it's actually a much, much smaller range that they're currently allocating to the different routing authorities. Now, the RFC technically says that any address that is being allocated in the network to an end host must have a 64-bit interface identifier that uses the EUI-64 addressing format. So this means that your end host or your router who actually has an IPv6 address assigned, they're always supposed to be /64. So even though that's basically half of the address range that is on a per subnet basis, this is what the end host would be looking for when they're trying to do the stateless auto configuration. So basically half of the address is going to be the network portion, and then the other half is going to be the host portion. Specifically in iOS's implementation, you can't technically configure it to be anything that you want, but for the actual end host, you should be assigning them as /64s. For the point-to-point links between the routers, you could technically use /127 for just two individual addresses. Ultimately, it depends on how you want the routing design to work. But for the end host, generally, they should have a /64 address for the network, and then they're going to figure out their end host interface ID based on the EUI-64 format. Now, specifically, this format is part of the addressing architecture specification in RFC 4291. There's a section towards the end in the appendix that shows you how to do the conversion into the EUI-64 address format. We'll take a look at this on the iOS command line. This is how the router automatically originates or automatically assigns a link local address on a per interface basis, or if you are doing automatic assignment of the interface ID or you're doing stateless auto configuration, this is how the router is going to figure out what the end host address should be. So in the case of an Ethernet LAN that we are assigning an IPv6 address on, it's going to take the 7th most significant bit of the address, which is called the universal local bit. It's going to flip this bit, so it's going to invert it from either a 0 to a 1 or a 1 to a 0, then add padding that is FFFE in the middle of the address. Because the problem is an Ethernet MAC address is only 48 bits long, so we need to get up to 64. So by adding the additional 2 bytes into it, we can get to a 64-bit interface identifier, which is going to allow us to have a subnet mask of /64 at the link level. Now, we'll see design-wise, the potential problem of doing this is that it gets very difficult to keep track of in the network what are the actual addresses of the end hosts in the topology. So for a real implementation, when you're numbering your routers, usually it's probably not a good idea to use the EUI-64 address unless you have some sort of external mapping table or maybe DNS set up that you can quickly figure out what are the particular addresses that correspond to the routers. Because otherwise, we're essentially going to have to keep track of what is the MAC address of the router. And if there is a change in the MAC address, let's say, for example, one of the line cards on the router fails and we need to swap it out, it means that the end host address is going to change. So this could potentially then affect our filtering or our routing design in the topology if the router's address is changing. So again, technically the RFC says that you're supposed to automatically assign this, but from the actual iOS implementation point of view, you can do it however you want. Now, another key point that we'll see here that has changed with IPv6 is the neighbor discovery process that is now part of the ICMPv6 stack, which is essentially a replacement to the address resolution protocol. Now, the reason that this is important is that with IPv4, ARP was kind of an afterthought, where it's technically a separate protocol that is unrelated to IP. When we look at it from a layer 2 point of view, IP uses the layer 2 protocol type code 0 by 800, where IPv4 ARP uses 0 by 806. In the case of IPv6, this is already built in for us through the ICMP stack. So in the case of Ethernet, this is going to be 100% automatic for us. The only time that we would really need to worry about this is if there's some sort of filtering that is blocking the ICMP neighbor discovery process, then the routers would not be able to resolve their IPv6 addresses to their Ethernet MAC addresses. Additionally, just like we saw in IPv4, there's some design problems we need to think about when we are running the protocol over multi-point non-broadcast interfaces, which in our particular case would be a multi-point frame relay link. But the same design case would be if we were running it over multi-point ATM, or if we had legacy ISDN dial-up, and we were trying to run IPv6 over that. Now, technically, there is a specification for inverse neighbor discovery, which would be the equivalent of inverse ARP for frame relay. but I don't believe that Cisco iOS actually implements this even in the newest versions. So we'll see the end result of this is that for multi-point non-broadcast interfaces, we always need to provide a static layer 3 to layer 2 mapping for the IPv6 stack. Now, this is going to be the same exact logic as we saw previously with the frame relay map for IPv4, which is going to resolve our local layer 2 address to our remote layer 3 address. And in the case that we want to send multicasts over the link, we would need to tell the frame relay interface to support pseudo broadcast for that particular circuit. So similar to IP version 4, where RIP is using the address 224.009 for IPv4, then IPv6 is going to use FF02::9. So this means that if we were running RIP-NG over frame relay, just like if we were running RIP version 2 over frame relay for IPv4, not only would we need our unicast layer 3 to layer 2 mapping, but we would also have to make sure that broadcast support is included. So let's take a look at this basic process on the command line where we're enabling IPv6 routing on the Ethernet segment and then also on the non-broadcast multi-access segment. And we'll look at the differences in the automatic resolution through the ICMPv6 neighbor discovery. So the topology that we're using for IPv6 is essentially the same as the previous sections, where I have the transit network here configured as 155.28.yy.y, where y is the router numbers. So for example, between routers 1, 4, and 6, this would be 155.28.146, where router 1's address is .1, router 4's address is 4, router 6's address is .6. Now, to keep the IPv6 addresses a little bit easier to keep track of, I'm going to use the same type of addressing structure, but it's key to note that since I'm using what previously was decimal numbers in a hexadecimal notation, in binary, it's not going to be the same values. So even though the addresses are going to look similar, when we look at the address that is 2001:155:28:146:1/64, in binary, this is a completely different address than IPv4's equivalent, 155.28.146.1. So within the scope of the lab exam, this is one of the big issues that you need to be aware of with IPv6, that if you make a mistake in the addressing, then it's going to cause a lot of problems in the upper layer protocols, and it's very unlikely that you would get credit for those particular sections. So definitely double check and triple check your work to make sure that you're not transposing any of the digits, because minor mistakes like that can really cost you a lot of points within the scope of the exam. So let's now take a look at the command line between router 1, 4, and 6, and we will configure IPv6 on their LAN interfaces. Now, before I do this, it might be a good idea just to test my basic IP version 4 connectivity to make sure that there's no underlying problems in the Ethernet LAN or in the frame relay non-broadcast interfaces, because I don't want to be troubleshooting something in IPv6 that ends up to be a lower layer problem, like simply the interface being shut down or the VLAN is not correctly assigned. So on router 1, first thing I'm going to do is make sure I can ping 155.28.146.4 and 6. So this is routers 1, 4, and 6 over the LAN. Now, before I actually enable the IPv6 protocol, I'm going to turn some of the debugs on so we can see exactly what's going on with the ICMPv6 neighbor discovery process. We're going to look at the debug IPv6 packet detail and the debug IPv6 neighbor discovery. Next up on router 1, let's go to the LAN interface here, which is fast Ethernet 0/0. I'll configure an IPv6 address that is 2001:155 colon 58, or actually 28, 28 colon 146 colon 1 slash 64. Now we can see as soon as I assigned the prefix, the router automatically starts running the ICMPv6 neighbor discovery protocol, which is going to do a couple different things for us. First and foremost, it's going to run the duplicate address detection feature to make sure that I have not assigned an address that someone on that same particular link already has. Now in IPv4, we can kind of indirectly figure this out if we hear an unsolicited ARP reply, which is called a gratuitous ARP, for the same address that we have assigned. Based on this, we can assume that someone has a duplicate address configured as us. But in the case of IPv6, there's a specific question and answer protocol, which is the duplicate address detection for ICMPv6 neighbor discovery, that if the address is not unique, it's not going to allow the router to assign it there, or it's not going to allow the end host to assign it. So once router 1 figures out that no one else has this address assigned, it says through ICMP neighbor discovery, I'm sending a neighbor advertisement, or the NA, for my particular address on fast Ethernet 0/0. This is the equivalent of the IPv4 gratuitous ARP. So it's essentially an ARP reply that someone did not ask for. We're doing this in order to update their basically ARP cache so they know what MAC address corresponds to my local IPv6 address. Now, additionally, if we scroll up a little bit further, we'll see the first thing that router 1 did was to add the prefix that we assigned to the link and then elect a link local address, which here is FE80 20D BCFF FE1F 8C00. So again, anything that starts with FE80, this is not routable between the interfaces on the device. So it's only locally significant between the devices on that particular LAN. Now from this format here, we should be able to infer what the MAC address that router 1 has assigned on its interface. So if we were to look at this EUI-64 address, and we have actually one leading 0 that's not showing up there. If we were to take the first byte, which in this case is 0x02, and look at this in binary, which is 0000, 0010, and then we were to take the 7th most significant bit, so we have 1, 2, 3, 4, 5, 6, 7, 8. We take the 7th most significant bit and invert this. So now this becomes 0x00, which is 00000000. Then remove the padding that is FFFE. So we essentially now have 000D BC 1F 8C00. We should see that this should be the MAC address that router 1 has assigned on its fast Ethernet 0/0. So we can see its value there, 000D BC1F 8C00. So automatically, as soon as we start running the IPv6 process, the router is going to generate a link local address, which is FE80, plus the address that is derived from the MAC address. Now, the key point here is that this is going to be used for the automatic address configuration. So for any hosts that are on our link, they're not going to be manually assigning what their IPv6 addresses are. If we look at router 1 and look at the show IPv6 interface fast Ethernet 0/0, it says that right now we have this particular link local address assigned. We have this global address assigned. This is the particular prefix. So right now we have a 64-bit network portion. We have a 64-bit host portion. The actual full address here for router 1, if we were to include the zeros, would then be 2001:55:0028:0000:0000:0001. So this would be our full 128-bit address. We can see that by default, the router is going to show the short notation for this, where it's going to take the maximum number of zeros and then replace that with the 2 colons. So you'll see in cases where there are multiple sets of zeros in a row, the router's only going to be able to use the double colon notation once. Because if we said 2001::155::1, we essentially wouldn't know how many zeros did we delete in the first portion of the address versus how many zeros did we delete in the second portion of the address. So we can see once I type that address in there, the router is actually configured with the transport input telnet command by default, which means that we are going to, if I type an address in there, it's going to try to telnet to the address. Actually, it's transport preferred telnet. So if I wanted to turn this behavior off, and sometimes this could be useful if you want to keep DNS resolution on, but you don't want the router to automatically telnet when you mistype a command, this would be under the console. You would say transport preferred is none. So by default, the preferred transport is telnet. So now if I type that address in, the router's not going to try to telnet to it. But it still would allow me to do DNS resolution if I still said IP domain lookup. So kind of unrelated to IPv6 there, just a side note to keep in mind. Now again, if we look at the show IPv6 interface, fast Ethernet 0/0, right now the router does not have IPv6 unicast routing on. So we see that it is not sending ICMP-ND router advertisements, or the RAs. Right now, essentially, router 1 is just an end host for IPv6. We are not announcing ourselves as a router, and we do not have ourselves configured for auto configuration of hosts on the link. In order to do this, we would have to turn the routing process on. So just like we have IP routing on, we need to simply say IPv6 unicast routing. Once we do this, we can see that router 1 starts to announce itself as a router. It says it's sending the ICMP neighbor discovery router advertisement to the all host multicast, which is FFO2::1. Router 1 saying the MTU of my link is 1500. This is the prefix that you could use for autoconfig. And this is the specific time that you can use it for. So you can configure a priority between the routers if you want to try to prefer one over the other. This is kind of like a lightweight version of DHCP. So we cannot use this to assign options like DNS server or the other DHCP options like the call manager server for our IP phones. For that, we're still going to need DHCPv6. But for just an address assignment and giving the end host a default gateway, stateless auto configuration is going to automatically do that for us. So now let's go to someone else on the LAN. Let's go to router 4. And instead of manually assigning an address to the link, let's simply say on fast Ethernet 0/1 that the IPv6 address is going to come from autoconfig. So now we should see on router 1 that there was a router solicitation being sent which essentially means that router 4 was asking router 1 that it wants an address to be assigned. So once router 4 enables the IPv6 process on the interface, it means that it's automatically going to choose a link local address. So in this particular case, the link local address of router 4 is FE80::21A 6CFF FE6B, etc. This router solicitation that comes in, this is essentially an ARP request just for the routing devices on the segment. So this is different than the neighbor solicitation, which is the NS. The neighbor advertisement and the neighbor solicitation, those are like the ARP request and the ARP responses. The router advertisement and the router solicitation, those are ARP requests and responses that are specifically for the routing devices on the network. So if we now look at the end result of this on router 4 and look at the show IPv6 interface fast Ethernet 0/1, we could see that it did learn the prefix 2001 155.28.146. It says stateless address autoconfig is enabled. Our end host 21A 6CFF, etc. This is coming from the MAC address of the interface. So again, if we were to do the reverse conversion here, it essentially means that router 4's MAC address should be 001A 6C 6B D3 9B. If I show interface fast Ethernet 0/1 and include the burned in address 001A 6C 6B D3 9B, so we can see that's a match there. Now again, it's really not going to matter what the end host of the address or the address of the end host is if this is not a routing device. The problem is that if you're trying to keep track of who are the routers versus the end hosts, most likely you wouldn't want the router's address to be dynamic. So the same reason you normally wouldn't have your router learning an address through DHCP for IP version 4, you generally would not want to do the same thing for IPv6. So once the router turns unicast routing on, it's automatically going to start sending those router advertisements. Then any of the end hosts on the interfaces, they would automatically learn the prefix from the router and then basically use it as a default gateway. So we can see now that I turned IPv6 unicast routing on, router 1 says I'm sending router advertisements every 200 seconds. The router advertisements are live for 1800 seconds, which is basically the idle timeout. Then we could change the specific attributes for the stateless auto configuration. If we go to the link level and look at the IPv6 neighbor discovery, IPv6 ND, the advertisement interval, this would be to say how often we're going to send the advertisement. We could change this with the RA interval. So if I say I could send it every 5 seconds, the RA lifetime would be how long is that valid for. If I did not want to send the advertisements, I would say IPv6 ND suppress RA. So let's say that there's multiple routers on the segment, but I only want one of them to be used as the default gateway. On the ones that I don't want to be used as the gateways, I would tell them to suppress the routing advertisements. So a lot of these general protocol things about IPv6, it would be assumed that you know this before you get to the exam. So a lot of this I'm not going to spend tons of time on today. There's a lot of good resources for this that you can see in either the Cisco documentation, in the RFC. There's a lot of good books on IPv6. One of them specifically that you may want to take a look at is the IPv6 Theory, Protocol, and Practice. Now, this is a vendor-independent book. So similar to that MPLS-enabled applications I was talking about before, This is IPv6 from a standardized point of view. What are the design problems they're trying to solve with it versus IPv4? What do the RFCs say that the implementation should do? It's not really going to focus on the specific syntax for Cisco iOS's implementation. Now, there are separate books on that talk about configuration of this on iOS. If you look for IPv6, Cisco iOS, you can see there's some other ones that aren't Cisco Press. There's one specifically that is, let's see, I think it's IPv6 configuration on Cisco iOS. Let's say Cisco Press. And it must be this one here, implementing Cisco IPv6 networks, which is pretty similar to the configuration guides, where it just talks about how do you implement the specific protocols in IPv6. So a lot of this configuration we're going to go over today quickly. But again, if you understand the IP version 4 counterparts, then it really shouldn't be that much further to get the IPv6 implementation. The biggest thing that most people have trouble with is to understand how the addressing structure works, and then to make sure that you don't make any minor mistakes when we're implementing the actual addressing on the interfaces. But as we can see here on the router's LAN interfaces, there's not really that much configuration you need to do. As long as you enable the protocol through ICMP neighbor discovery, the routers should automatically figure out who are the other devices on the link. Then if we send a packet to router 1, we can see we didn't drop one packet first, which is normally what you would do with IPv4, because the router waits for traffic to be sent before it sends an ARP request for the particular destination. In the case of IPv6, this address table is already pre-populated, because as soon as we turn the IPv6 stack on, the device automatically starts sending the neighbor advertisements. And again, that's the equivalent of the gratuitous ARP in IPv4, where it's an ARP reply without getting the ARP request to begin with. So next, let's take a look at an example of running IPv6 over the non-broadcast frame relay segments. So between router 1 and router 5, right now on this segment, we have, for IPv4, we have 155.28.0.0/24 assigned, where router 1 is .1, router 5 is .5. On router 1's end, this is configured to use a point-to-point subinterface. If we look at the show IP interface brief, this is serial 0/0.1. So similar to IPv4, point-to-point interfaces do not require layer 3 to layer 2 resolution for IPv6. So this essentially means the only thing I would need to do here is go to the link level and say IPv6 address. I'll say 2001.155.28:1/64. And essentially that's it. We're assuming here that there's not going to be any problems in the layer 3 to layer 2 resolution, because when the routing table points a packet towards serial 0/0.1, the router already knows that there's only one possible layer 2 destination. So it's always going to use circuit number 105 in the layer 2 frame that is being sent towards that interface. Now, on the other end of the link from router 5's perspective, this is a multi-point non-broadcast interface. So router 5 will need to know specifically what DELC number do I need to use in order to reach router 1. So first, let's turn routing on. Let's say IPv6 unicast routing. Then on the frame relay interface, we'll say IPv6 address 2001.155.28:5/64. If we were to look at the debug frame relay packets and debug IPv6 packets, we should see that when we tried to send packets out to router 1's address on the frame relay interface, the frame relay process is going to tell us that we do not know what is the layer 2 circuit number we need to use for that particular destination. So frame relay is saying encapsulation has failed because there's no map entry link. Basically means there's no frame relay mapping. IPv6 is reporting back that encapsulation is failing because it could not queue for resolution. This again means that there's a problem in the layer 3 to layer 2 mapping, the layer 3 to layer 2 resolution. So essentially what this means here is that we're missing the frame relay mapping. For this particular version of iOS, they do not implement inverse neighbor discovery. And like I said, even in the newest iOS versions, I don't think they have added support for it. So this means that on any multi-point non-broadcast interface, we always need a manual resolution for the next hop values of the IPv6 neighbors on the other ends of the link. So on router 5, we'll say to get to router 1, which is this address followed by a 1, we need to use circuit 501. And I'm going to assume down the road that I'm running some routing protocol, so I'm going to include the pseudo broadcast support. Now at this point, we can see that we do have reachability to router 1 using the global unicast address. Now we'll see this does not imply that I have link local reachability to router 1, which is going to be necessary once we actually run our routing protocols. So if this were point-to-point on both sides, either point-to-point subinterfaces for frame relay, or if we were to run IPv6 on the point-to-point serial link between router 4 and router 5, then we would not need to worry about the layer 3 to layer 2 resolution. The same thing with the Ethernet between routers 1, 4, and 6. Since the ICMPv6 neighbor discovery is going to take care of the MAC address to IPv6 mapping, we don't have to worry about any of the layer 3 to layer 2 resolution.